Massive Bob. Today we're looking at mechanics, circular motion in the horizontal plane, and in particular non-uniform circular motion, okay, as opposed to uniform circular motion where the angular velocity is constant. Now we need to have a quick look at some of the notations, I guess. So first of all, we need to get used to some of the notations, because basically the dots represent time derivatives. I think that's the easiest way to say it. Okay, that the one dot means the first time derivative, and the second dot means the second time derivative. So it's like acceleration, velocity, acceleration. You can see here x double dot is the second derivative of displacement with respect to time, and the x dot is the first derivative of displacement with respect to time. We could also say that x double dot is the first derivative of the x dot as well with respect to time as well. We could say it like that. But y double dot obviously follows the same idea, that it's a second derivative, and in this case the y double dots and the x double dots are actually our x and y components of acceleration, and the y dots and the x dots are the x and y components of velocity. But theta dot obviously is omega, given the symbol omega, which is the change of angle with respect to time, or d theta dt. Okay, that's, in uniform it's constant, in non-uniform it's not constant. Theta double dot is actually obviously the second derivative of theta with respect to time, or the first derivative of theta dot with respect to time, or because of the notations you could say it's the omega dt or omega dot that is equal to theta double dot. Okay, so theta double dot is actually equal to omega dot. Okay, so there's some notations we have to get used to basically, but these are all time derivatives, and as I said, just think of one dot first time derivatives, two dots second time derivative, not too bad. Now where do we start? Well, we start the same place as we do with uniform circular motion. Let's have a look here. Let's see if I can get these pins to work here. It might work there. Okay, let's try over here. Okay, so basically it's okay. Here we go. I have to draw this with a mouse. It's a bit tricky sometimes. Okay, so what do we do? Well, let's have a look. First up, we where are these components coming from? Well, they're coming obviously from the x and the y components at this point. Basically, it's traveling in a circle. It has a component acting in the x and the y basically direction. Okay, so that's the if you like, its displacement in terms of x and y. That's its x component, its y component. That will give us arrive at that point A there. Okay, that's it, with x and y components like that, basically. Okay, so let's have a look now. What do? Well, we have to differentiate each of these with respect to time, and the only thing that does change is the theta, so that's why we have to differentiate cos theta with respect to time. But as you know, we have to use implicit differentiation or function for function rule, differentiate it with respect to theta first, and we get a d theta dt on the end, which is theta dot, and the derivative of cos is minus sine, so we end up getting that theta dot is equal to minus r sine theta theta dot. So that's the x component of the velocity, the displacements, x displacements derivative basically. So the y, we do the same with the y. The y component of its displacement, I guess you could say, is basically dy dt. We end up getting, obviously we differentiate sine theta with respect to theta, and have a d theta dt on the end, which again is theta dot or omega. And we end up getting that y dot is equal to, you can see here, r cos theta theta dot. So these are the x and y components, if you like. I've marked them over here. You can see here. Let me see if I can just get this again. Okay, you can see here. This is the basically the this is the y component, and the x component is you can see here is minus r sine theta theta dot, and the y is, you can see here, r cos theta theta dot. So these are the x and y components of acceleration. Okay, so let's move on now to the if you like, the horizontal and vertical components of the acceleration. So how are we going to get them? Well, I mean, we're at one dot. We've got to go two dots, I guess you could say. So we've got to differentiate them again. But the only thing, obviously, is that theta dot now is not constant, so it's going to have its own derivative, theta double dot. And that's going to basically mean that we're going to have to use the product rule, okay, because we have theta and theta dot changing, if you like. Okay, so we are going to use the product rule, and as you probably know, the product rule is the first by derivative of the second plus the second by derivative of the first. So it's a fairly easy rule, but we just need to make sure we use it correctly here to get the x double dot. So it's basically minus r sine theta by theta dot's derivative, which you'll see in a minute is theta double dot, and you can see here it's the basically the minus r, if you like, theta dot by sine theta's derivative. So, or you can just say it's just theta dot by the derivative of r sine theta, which is dd theta. You can see down here. Again, we've got to use the well, chain rule or just differentiation, okay, to do this. Okay, so we need to basically go dd theta or sine theta, and we get a d theta dt next to the theta dot. Now, obviously, that gives us theta dot by theta dot, which is actually theta dot squared. So we end up getting that x double dot is equal to minus r sine theta theta double dot minus r cos theta theta dot squared. Okay, so you can see this is obviously different now to the uniform circular motion case, where obviously yeah, we end up getting that well, if theta dot is constant, then theta double dot must be 0. Okay, so anyway, I won't mention that now, but this is basically the non-uniform circular motion case we're looking at the moment. So y dot, again, we have two functions, cos theta or r cos theta and also theta dot. They're both theta and theta dot are both changing with respect to time, therefore we use the product rule again, and we do the same sort of thing, and we end up getting what, d theta dot dt theta double dot, and we also get a d theta dt, you can see here, by theta dot. That's going to give us the theta dot squared, and again that theta double dot would be 0 in the uniform circular motion case. Okay, alright, so we now have the if you like, the x double dot and the y double dot, which are basically the x and y components of the acceleration. Right now, okay, so we're well on the way. Okay, so what do we have to do now? Well, we have to resolve them radially or normally, if you like, and also tangentially. So we have to resolve these things and get the components. Now, I always say, if you're going through the angle, remember, always going through the angle, you are getting the cosine of the component. Okay, well, you get the a particular, if it's a vector, it's going to be, or a force, it's going to be that force times sine theta or cos theta. If it's going through the angle, I said it should be cos. Okay, so let's have a quick look. What are we doing? Well, we've got y double dot, and we have to resolve along these red lines. These red lines are the radial or normal. I think I've actually written it as normal components actually in the next section. But basically, those red lines are, we have to basically get, you can see here, y double dot sine theta. That's going through the complement of the angle here. And we're going to get x double dot cos theta because it's going through the angle, and they're both acting in the same direction. Okay, so we have, if you like, the x double dot through the angle, which is the x double dot times cos theta, and the y double dot through the complement, which is y double dot sine theta. So we actually have to get these expressions, the y double dot and the x double dot, and multiply them by the y double dot by sine and the x double dot by cos. Okay, so I'll just see here over here. So resolving radially or normally, we get x double dot cos theta and y double dot sine theta. Now, when we look at this, we basically get a few components which are going to basically cancel each other out. So I'll just try and make this a little bit bigger so we can actually see. Okay, alright, so in this particular, okay, so I'll just try and get this to move now. Here we are. Okay, so we end up getting minus r sine theta, theta double dot minus r cos theta, theta dot squared times cos. Actually, that's x double dot, obviously, and the plus the other expression there is y double dot times sine theta. And you'll see that some bits will cancel when you multiply that out, and you end up getting a sine squared theta and a cos squared theta with an r. So we end up getting that the radial or normal component of the acceleration is minus r theta dot squared or minus r omega squared. Now, the negative obviously indicates that it's actually in the opposite direction, which is actually towards the center, which is hopefully something we actually did know, that the obviously the centrifugal forces does actually act towards the center of the motion, actually of the well, it's a circle. Obviously in the circular motion, there's a center, so it's acting towards the center. Okay, all right. Now, what happens now? Well, the first thing is that you can see here that we've got a tangential and a normal component to the acceleration in non-uniform circular motion. There actually is a net acceleration, you can see here, which is just using vector addition, which is acting a little bit above the center of the circle, you can see here. And basically, this net acceleration, okay, is basically the acceleration of what's felt by the particle if it's traveling in what's called non-uniform circular motion. So it's got a component this way and a component that way, and basically it's has what's called a net acceleration, which you can see here is not in either of those two directions, tangentially or normally. Now, let's look at our example. Now, our example is a bit similar to the one we did in what's called the uniform circular motion. Okay, about this gravitational wave, which is just been, as I said, recently discovered. Basically, we've been hit by a gravitational wave that started to accelerate the Earth. Okay, wow. In fact, it's a fairly powerful one by the look of this. Okay, so it gave us, if you look here, our tangential acceleration at 762 meters per second per second. Okay, so we're really moving, we're really accelerating. Basically, in our last example, you might remember I just said that roughly 8 kilometers per second would actually see us flung off the Earth in about 10.5 seconds. But I'm just going to go through now how we get that 8 kilometers. And so basically, what have we got to do? Well, we've got to overcome this normal component to the acceleration, basically, which is gravity. Okay, so we need to overcome gravity. And I'll just say n. You can see here written it as the normal component, and it's basically 9.8 meters per second. And we use, well, v equals r omega, the linear velocity expression and we basically rearrange, well, we make omega the subject as v on r, and then we plug it into an equals r omega squared, and one of the r's cancel, and we end up getting that an is equal to v squared on r. So this is the normal, or the radial component of our acceleration is actually v squared on r. Now, if we set these equations up, let's see down here, and we let that 9.8 equal v squared on r, then we solve it for v, basically, and we end up getting the velocity at which we overcome, if you like, gravity. Okay, so the normal component will disappear, and our net acceleration will become tangential, so we'll be flung off at about 7.9 kilometers per second. Okay, that's our instantaneous linear velocity at that particular case. Okay, so you can see here we're going to be flung off the surface. We have to overcome the normal component, and the net component becomes the tangential component. And if you do the acceleration formulas, you can see here it's only about 10.5 seconds it takes for us to become flung off the Earth tangentially. But as I was saying, that not only will we be flung off, everything else, and I was speaking to someone, and they said actually pieces of the mantle would also be flung off as well. So the buildings and cars and water and everything would be flung off. So it would be a pretty scary scenario. Anyway, and hopefully that will never happen. But thank you for watching, and bye for now.